Hello everyone, this is Amit Brahmbhatt, your instructor at BCCS, Laurel Ridge College. And today we are going to go over Chapter 12, Information Systems. Let me go ahead and share my screen. Okay, so welcome to Chapter 12, Information Systems. In this chapter, we are exploring how computers help us store, manage, and analyze information, something that has become essential in every industry today. We'll look at spreadsheets, databases, SQL, big data, e-commerce, and more. As we go through the slides, I'll point out real examples you see every day, like online shopping systems, school gradebooks, medical databases, and even data behind your social media apps. By the end of the chapter, you'll understand not just how information is stored, but how it's organized, processed, and transformed into something useful for decision making. We have several key goals. We'll explore the role of general information systems. These are the systems designed to collect, store, and process and distribute information. Then we'll learn about how spreadsheets work, including rows, columns, cells, formulas, and built-in functions. You'll also see how to design spreadsheets so that they are flexible and can grow with new data. After that, we'll shift to database management systems, software that handles large amount of structured data. We'll look at what makes up a DBMS and why databases are used instead of spreadsheets when data becomes more complex or needs to be shared. Our remaining goals focus on relational databases, the type used in websites, apps, and business systems. We learn how information is organized into tables, how records are linked across tables, and how to write basic SQL queries. We'll also introduce entity relationship diagrams, which visually show how data tables connect. Finally, we'll discuss e-commerce, how online buying and selling become possible, the technologies behind it, and challenges like security and privacy. All of these skills will give you a strong foundation for understanding how modern information systems operate. Managing information systems. Information systems are software tools that help us organize and make sense of data. This includes two major categories, spreadsheets and database management systems. Spreadsheet lets us work with smaller structured sets of data. Think budgeting, tracking sales, or analyzing statistics. Database systems handle larger, more complex data sets that must be shared, updated, and accessed by multiple users at once. The key idea is that information by itself isn't useful until a system helps us transform it, sorting it, calculating it, and using it for decision making. Spreadsheets. A spreadsheet is basically a digital grid made of rows and columns, where each intersection is a cell. Every cell can hold text, numbers, dates, or formulas. This grid structure makes spreadsheets extremely flexible. You can enter raw data, perform calculation, sort information, and create summaries. Spreadsheets use a labeling system like A1, B3, or C10 to identify cells, which lets formulas refer to different paths of the sheet. This combination of structure and simplicity is why spreadsheets are used so widely in business, education, finance, and even scientific research. In this example, we are looking at data collected over several weeks, such as how many students visited tutors. The power of this setup is that the spreadsheet lets you store both data and calculations side by side. As new weeks are added, formulas automatically update totals or averages. This helps you spot trends over time, like whether tutoring demand is increasing or decreasing. It also highlights why spreadsheets are useful for small scale analysis. They are easy to update, adjust, and use for ongoing monitoring. Formulas are what make spreadsheets powerful. Instead of typing results manually, we store a formula inside a cell, and the spreadsheet automatically displays the calculation. If underlying data changes, maybe a number is wrong, or you add new values, the formula recalculates instantly. This ensures accuracy and saves time. Spreadsheets support basic math operations like addition, subtraction, multiplication, division. Setting up formulas correctly means you can easily scale the sheet later if you add more rows, columns, or categories. This slide shows actual formulas behind some cells. Instead of seeing the computer value, you can view how it was calculated. For example, a formula might sum a list of weekly totals or compute an average. Understanding this view is important when auditing or debugging a spreadsheet because it lets you confirm logic is correct. You learn how cell references move with formulas, how to freeze certain cells using absolute references, and how to create formulas that adapt as you expand your data. In addition to basic arithmetic, spreadsheets come with built-in functions such as sum, average, min, max, and count. These functions make your formulas shorter, easier to read, and less error-prone. Another important term here is a range, which refers to a continuous block of cells like A1 to A10 or CF to F3, C3 to F3. The ranges are useful when writing formulas because they let you apply functions to large sections of data at once. Understanding formulas and functions is essential for building efficient spreadsheets. Here we see some of the most common functions you'll use in spreadsheets. Sum adds range of values, average computes the mean, count tells you how many cells contain numbers. There are also logical functions like if, text functions, and date functions, all of which help you perform more complex analysis. As your data grows, functions become essential for keeping your spreadsheets manageable and automated. A circular reference happens when formulas depend on each other in a loop. If cell A1 uses B1 and B1 uses A1, then it will error out. When this happens, spreadsheet can't find a final value. It cannot calculate one, and it keeps going in circle. Here's an example of circular reference that cannot be resolved. And most of the spreadsheet programs would warn you when this happens. And understanding how to structure formulas to avoid circular dependencies is important for building reliable spreadsheets. So think of 7 tasks a spreadsheet might be used for. Common uses include budgeting, inventory tracking, data logging, forecasting, scheduling, and more. Spreadsheets are extremely versatile. They are used anywhere people need to store numbers and analyze patterns. Later, slides provide sample answers, but at this point, the main idea is to think creatively about how spreadsheets can help organize information. Here we see an example tasks of spreadsheets can help with tracking sales, analyzing sports stats, maintaining student grades, logging car maintenance, summarizing travel expenses, managing project schedules, and planning stock purchases. These examples highlight how spreadsheets help transform raw data into useful summaries. They're especially helpful when you need dynamic calculations or when your data changes frequently. Here, this slide highlights concept of what-if analysis. This is when you change certain values in the spreadsheet to see how it affects the outcome. For example, what if attendance drops by 10%? What if prices increase? What if materials costs are cut in half? Because spreadsheets update instantly, you can test multiple scenarios quickly. This makes spreadsheets powerful for planning, budgeting, and strategic decision making. Spreadsheet can also generate charts and graphs, which turn raw numbers into visual insights. A graph can reveal trends, patterns, and comparisons that might be hard to see in tables. Bar charts, lines, graphs, and pie charts are common examples. Visualizations help communicate findings to others, making the data more accessible and easier to understand. A database is a structured collection of data, and database management system helps you store, manage, and retrieve the data efficiently. It includes three main components: the physical database, which is the actual stored data, the database engine, which processes requests, and the database schema, which describes the structure of the data. Databases are used when the data becomes too large, too complex, or needs multi-user accounts. Situations where spreadsheets aren't enough. If we expand on DBMS components, database engine handles reading, writing, updating, and security. The database schema outlines how data is organized into tables, fields, and relationships. A database query is a request for information, such as finding all customers who rented a movie. Understanding these components helps you see why databases are essential for large-scale information systems. Here we visualize DBMS structure. It shows how physical files, engine, and schema work together. The user interacts with database through queries or applications. The schema ensures that data is consistent and well organized, while the engine controls how data is stored and accessed. This separation makes databases powerful, scalable, and secure. In a relational database, information is organized into tables. A table consists of records, also called objects or entities, and each record contains fields, which are attributes describing that record. For example, a movie record might include title, genre, rating, and ID. Relational databases allow tables to link each other through shared fields, enabling complex queries and relationships. How do we uniquely identify a record? Answer is with a key. The example shows a movie table where each movie has a unique identifier, usually a movie ID. Keys ensure that there are no duplicates, and they let other tables reference specific records. Without keys, database relationships wouldn't work. Here, this slide explains that a key can be one or multiple fields that uniquely identify a record. The schema example, movie ID, which is a key, and title, genre, rating are the other fields in the table, shows how the structure is formally described. Schemas define what data is stored and how it must be formatted, which keeps the database consistent across all users. Here we see a customer table with fields like ID, name, and address. Each row is one customer, and combined with movie table, we can link customers to the movies they rent, which leads into relational connections. Understanding individual tables is the first step for building relationships between them. How do we relate movies to customers? The answer is through linking table. In this case, a rents table. This table might include customer ID and movie ID, allowing the database to track who is renting what. Relationships like this make relational database powerful because they avoid storing duplicate information while still connecting data across multiple tables. Oops, let me go back. Structured query language, SQL. It's a language used to interact with relational databases. The basic format is select fields from tables where conditions. For example, the query shown retrieves all PG-related movies. SQL allows you to filter, sort, search, and retrieve data with precision. You learn to write simple queries that help answer specific questions about the data. Here we see three SQL queries, and uh, the slide asks what each one of them returns. I'll suggest that you pause the slide and try to answer it yourself. Well, the first one retrieves names and addresses from customer table. The second one finds all action movies using wildcard pattern. And the third one selects all R-rated movies and orders them alphabetically by title. These examples illustrate how SQL helps you extract meaningful information from large datasets. Modifying database content. Here we see SQL statement that insert, update, and delete data. The insert adds new customer record. The update changes the genre of specific movie, and delete removes all movies rated R. These commands are powerful and must be used carefully because they permanently change the database. Understanding them is essential for database management. Database design. Here in this slide, we learn about entity relationships or ER modeling, a technique used to design relational databases before building them. An ER diagram shows entities such as movies or customers and the relationship between them. Cardinality constraints describe how many connections can exist, like one customer renting many movies or movie being rented by multiple people. How many movies can a person rent? I suggest you pause the slide and look over the diagram for movie rental database. It'll help you understand how many people can rent the same movie. The ER diagrams shows many-to-many relationship represented through the rents table. ER diagrams help designers visualize structure, relationships, and constraints before implementing the actual database. Here, this slide asks several questions about e-commerce. Common examples include Amazon, eBay, Walmart, Etsy, etc. E-commerce became feasible due to secure payment systems, widespread internet access, and advances in web technology. Challenges include privacy concerns, cybersecurity, shipping logistics, and competition. Understanding e-commerce helps you see how data and technology support modern businesses. Big data. Big data refers to data sets that are too large, fast-changing, or complex for traditional spreadsheets or databases. These data sets may include video, audio, sensor data, or millions of records generated by minute. Big data technologies allow organizations to analyze patterns at a massive scale, powering applications like recommended systems and traffic analysis. Big data offers major benefits, improving business decisions, predicting trends, supporting healthcare analytics, and enhancing public safety. It also creates challenges. Large volumes of multimedia data require huge storage capacity. Organizing the data and processing it efficiently can be difficult. Security is also a major concern, as big data often contains sensitive information. Understanding these challenges helps organizations manage data responsibly. Here the slide lists several questions about political use of internet. The $100 revolution refers to inexpensive tools that allowed small donors to influence elections. In 2008 and 12, candidates used social media for fundraising and communication. Donald Trump relied heavily on Twitter during and after the 2016 and 2020 elections. These examples show how technology transforms political engagement. raising ethical questions about misinformation, privacy, and influence. The slide asks which software product earned the Hopper Award in 1981 and was intentionally not patented. You should look it up by yourself. And the answer is VisiCalc, the first spreadsheet program created by Dan Bricklin. His work revolutionized personal computing by turning computers into practical business tools. This also shows how not proprietary software decisions can shape entire industries.